All right, this is Physics 1B for November 16th. Today we're talking about the topic discussed right there. We're going to talk about the efficiency of a Carnot engine and do some calculations and problems with those. And then we're going to be talking about entropy, which is basically like a measurement of randomness. All right, so this was the Carnot cycle. We talked about it last time. We didn't really do any calculations with it. We just kind of set it up. The idea of a Carnot engine is that every portion of this process is irreversible, which means that, well, it means certain things about it. It means it's kind of like the most efficient engine you can possibly design, because there's no kind of heat loss to the surroundings, and yeah. And so we want to calculate the efficiency of this engine, knowing what we do about each of these steps right here. And just to kind of go through the steps again, we discussed them kind of briefly at the end of class last time. If we start at step 1, we've got some kind of a gas. It's placed in thermal contact with something that can produce, that can provide heat to it. It undergoes an isothermal expansion, which means, isothermal means same temperature. Each of these lines, the blue lines here, are isotherms. So if you go from A to B, the temperature doesn't change. That means that the heat goes into the system, and the system is going to do work by the expansion of the piston. Step 2, so this is isothermal. That's the main thing that we're going to say about it when we calculate things. Step B, the object is removed from the heat source, and then it expands on its own. This expansion is adiabatic, which is kind of impossible, but the whole point of this engine is to define like the most efficient engine possible. So adiabatic, of course, means it doesn't exchange heat with its surroundings. That means that there's no friction with the piston, which is obviously ridiculous, and also means that the walls of this container are perfectly insulated, which is also impossible. But imagine that it's adiabatic, and that would mean that there's no heat exchange, but the work, again, is positive here. We then take the same system, you put it on top of a cold reservoir. The goal is to basically get back to the initial state so we can complete their process and make it cyclical. So that means that we need to extract heat from the system by placing it onto a cold reservoir. That is just basically, in order for this to happen, this cold reservoir is going to have to pretty much be at the same temperature as the object, just slightly less temperature, slightly smaller temperature. So the idea here is that when we go from C to D, it's still going to be an isothermal compression. The cylinder's going to move, or the piston's going to move downwards, and then we take that and we remove it from the system, and in a way kind of like inertia or something, it continues to compress until it's back into the same original state right here. And again, this is an adiabatic compression process, because we've removed it from the place where it could have exchanged its heat. It can only apparently exchange. This is where these things are just so ridiculous, right? Because how is it that the system, right, is capable of getting heat in state 1, and where's the other place? In state 3, it's capable of ejecting heat, right? But yet, somehow, in steps 2 and 4, it's adiabatic, right? This is where you really have to use your imagination here, right? Because apparently, the bottom surface of our container, right? Think about this. The bottom surface is able to draw in heat, right? But the moment you remove it from a heat source, it becomes a perfect insulator. So it's like it's a perfect conductor of heat here, and then it's a perfect insulator of heat here. Can you guys see what I'm saying? Does that make sense?
Oh yeah.
So this is all very kind of like fairy tale engine, right? But that's the point of this. The point of this is we want to construct an engine in which every process is reversible. That's really important, and in which there's no heat exchange with the environment. And the point of studying this is to kind of understand the upper limit on how efficient an engine can be, if that makes sense, right? It's similar to the way I think in physics 1A, where you do a lot of problems with frictionless pulleys and pulleys that don't have inertia and stuff like that, because it can allow you to understand the theory in its kind of simplest form. And then once you understand kind of the ideal system, it's probably a little bit easier to understand the more complicated addition of loss of energy due to work and stuff like that, right? And it gives you the ability to kind of focus on what matters, right? In the case of moving objects and pulleys, it's like their energies, right? Their potential and kinetic energies. And in the case of these engines, it's going to be like the efficiency of the engine, right? Because it's It's a process where you're going in a cycle, and you want to understand how much energy you're actually getting out of it. Okay, so, or how much work can you get it to do for the given heat exchanges. All right, so let's go through and talk about the efficiency of this. This diagram is so big. So I guess I can make it a little bit smaller so we have a little more room to write here, and then I'll just scroll down so we have a little more room as well. All right, so we want to talk about the efficiency of this engine. Okay, so let us talk about the two isothermal processes, which are 1 and 3, okay? Okay, so if the working substance that's inside of here is an ideal gas, what we know for an isothermal process is that for an ideal gas, the internal energy only depends on the temperature, which means that for an isothermal process, the change in internal energy is equal to 0. So to take this back to our initial discussion of this, the first law states that, I kind of forget the way this works. Is this what it states? Delta U is equal to Q minus W?
Yeah.
Is that right? Okay. I always forget which one goes on the left, but this seems right to me. So if this piece is 0, then what we know is that Q is going to be equal to W. And let's talk about the QH part. So let's do process 1 first and say QH, the heat that comes in, needs to be equal to the work that's done by the piston here. So in that case, what we can do is on the right-hand side, we can use something that we've kind of already done. I guess I'll go through the steps again because I don't think it helps to do so. So to calculate this, what we really need to do is say the work done is going to be equal to PdV. That would be the infinitesimal work. So we need to integrate this. And if it's an ideal gas, the pressure that shows up inside here is nRT divided by the volume. It's an isothermal process, so the temperature could be taken out. N and R are going to be constants as well. So you end up just doing the integral of the volume. So then you'd be integrating between the two states. So what I'm going to do is I'm going to say the volume of this state here is VA. The volume of this state is going to be VB, VC, VD. And then they'll have the corresponding temperatures as well. So this is TA. This is going to be TB. I don't think we need to write down what the pressures are. This is TC. And then this one is TD, right? So if we're going for process here, where we go from TA down to TB, then this is going to be TA on the lower limit, and this is going to be TB on the upper limit. And then this is going to give us that the heat that comes in is going to be equal to nRT. And then when I do this integral right here, it's the integral of dV over V. So what's that going to give me?
Aren't we integrating over the volumes, though?
Oh, yeah, good point. Not temperature. Thanks. Sorry, that's kind of confusing. This should have been volume A and volume B. Thank you. Yeah, temperature's constant. We pull that out. R constant. So we're just doing dV over V. What's that integral going to give us?
Natural log of VB over VA.
That's right. And there we go. That's our QH for process 1. Let's do process 3 as well. So process 3 is going to be QC, and this is going to be going from TC up to TD. So we're going to end up basically skipping through the steps. We go nRT, and then we'll have a natural log now of the final minus the initial, right? So VD over VC. And then what we'll do is just kind of acknowledge that we can rewrite this, noting that, let's see, VD is less than VC. So if we want to get it so that the logarithm is going to give us a positive value, we could write it like this, negative nRT, and then let me erase that line. Times the natural log of, just flip the natural log, right? That gives you the same thing then. Okay. Anyone have any questions about that?
It's pretty straightforward.
All right. Next thing we can do is we could find a ratio of this. Oh, I did something bad here, actually. I didn't indicate what the temperatures are.
Yeah, wouldn't the temperatures be different?
Yeah. So on our diagram right here, TH is the temperature at B.
Wait, but it's isothermal.
Yeah. So I'm just going to go through this. So, like, let's look at this. So TA and TB are the same, right?
Yeah,
And
yeah.
then TC and TD are the same, right? So what I'm going to do is over here, I'll just say that we'll let TC be equal to TD because they are the same. And we'll say that that's going to be our temperature cold for the cold part of the cycle. And then over here, we're going to say, let's let TA be equal to TB, which is going to be what we call the temperature hot.
Okay.
So in our equations here then, where I wrote T for the hot process, we're just going to put a little H in here. And where I wrote T for the cold process, I'm going to put a little C in here. There we go. Okay, so now we can do a ratio. Yeah, let's do a different color so that it's clear we're doing something different. So now we could write the ratio, for example, of QC divided by QH. And a lot of things would cancel, but if we put QC on top, we're going to have TC times the natural log of VC over VD. And then in the denominator, we'll have QH, which is going to be TH times the natural log of VB over VA. And then I left out the minus sign. There's a negative sign right there, right? Okay, so we'll take that. We'll come back to that. We got to do the other two processes now. TH. Did I leave anything else off? I don't want to go too fast. All right. So now for the adiabatic processes, which is going to be 2 and 4. We worked out something earlier in the class where for number 2, for example, we can state that we can use this relationship we had that says that if I take TH and then I multiply by VB to the gamma minus 1, that this is going to be equal to TC, because we're going now from 2 to 3. So we're going from the T hot to the T cold. So T hot is going to correspond to VB, and then T cold will correspond to VC to the gamma minus 1. And then we'll put process 4 right here. So for process 4, we would just have, we'd be going from this one to this one. So we'd have the TC corresponding to the VD, to the gamma minus 1. And that should be equal to here. This is going to be TH. And then VA to the gamma minus 1. Does that look right? Oh, did I get all the subscripts right? Let's see. T hot goes with VB. T cold goes with VC. And then T cold goes with VD as well. And then T hot goes with TA. That looks right to me. Okay, so what do we use these for? Well, we have ratios of VC and VD and VB and VA over here. So what we can do is to use these equations to make a ratio as well. Looks like what we could do is basically put the THs on the same side. So what we could do is we could divide this equation by the equation on the right. So we would have on the left-hand side TH VA to the gamma minus 1. And then on the right-hand side, putting the TCs together or stacking them. Then the temperatures cancel. And the whole system is to the same power, which means you can get rid of the power as well. So you get a really nice simple relationship out of this, which is that VB over VA is equal to VC over VD. And then we take this and plug it into our equation up here to eliminate the logs, basically. I guess I can do that step just in case. So this tells us then that we get basically negative Tc over Th, and then the log of Vc over Vd can be written as just the log of Vb over Va. It kind of shows you why we pulled the negative sign out earlier, just so we get the same ratio in both cases. So now all of those cancel out, these and these, and we're just left with a really simple result, which says that QC over QH is equal to negative TC over TH. Now, why does the negative sign show up here? Can anyone remind me? Why would you... I mean, quantity of heat, why would there be a negative sign on the right-hand side? Temperature is obviously positive always, right? So why would the ratio here be negative? Is one of these quantities negative? Is QC or QH, can they be negative? How do we define Q as being positive and negative? Does anyone remember? Heat in is positive, yeah, exactly. So QH would be a positive quantity, QC would be a negative quantity, okay? Now, we can, of course, get rid of the negative sign. Yeah, and then John's saying the same thing. That's right. So we can get rid of the negative sign if we just write absolute values here. This would just then be equal to Tc over Th. Now, our goal here was to find efficiency. That's what we were doing. Efficiency of a Carnot engine. We do all of his thermodynamic calculations, right? We ended up getting to this. Why is that relevant? Well, because when we defined efficiency earlier, we basically got a relationship that was something like this. The efficiency of an engine was equal to 1 minus the absolute value of QC over QH. That was one way you could write it. So in this case, what we're going to get is basically just 1 minus the ratio of the temperatures. So in a Carnot engine, that defines what the efficiency is. The ratio of temperature cold to temperature hot is going to be what, defines the efficiency of your engine, basically. It's just about temperatures now. It's a little easier to understand, I think, than the left equation, mostly because temperature is something I think we all have a kind of decent understanding of. Now, if we think about the way this was all set up, and we kind of try to understand something about the efficiency of our engine here, right? The whole point of the way this was done here was to make these two temperatures extremely close to each other. The idea being that it would be easier to make the whole goal of Carnot engine is a reversible engine. And that required that every step was reversible, which in a way meant that we kind of needed these temperatures to be close to each other, right? So what does that mean about the efficiency of this engine then? If these two temperatures are really close to each other, what's the value of the efficiency going to be? Like, let's say that temperature C is like 270 Kelvin and temperature H is 280 Kelvin. What would the efficiency be? Is it going to be big, like 99%? Is it going to be small, like 1%?
It would be near zero.
Yeah, it'd be really small, right? It'd be really small. All right. But in general, what we can say is that that no engine can be more efficient than a Carnot engine operating between the same two temperatures. Sorry, I need to erase that. So this is in a way kind of another statement of the second law of thermodynamics. But it tells you something about, this is kind of like the upper limit on efficiency. So even though the number we got was really small, that was just because we assumed that we had to make these two close to each other. Now assume that we don't, and our cold temperature, let's say, is very close to absolute zero, like 10 Kelvin, and our hot temperature is something like, just normal 300 Kelvin, like kind of like normal temperature, right? Then all of a sudden your efficiency is huge, right? If the numerator is 10, the denominator is 300, you're going to get an efficiency that's very, very big in the upper 90% range, right? So what the Carnot engine efficiency kind of definition tells us is like the upper limit on the efficiency of an engine that you could have. An engine that has irreversible processes would automatically have a lower efficiency, basically, because every irreversible process would represent kind of a heat loss from the system, right? If you don't have adiabatic expansion in step 2, but instead you have some kind of exchange of heat with your environment, then the efficiency of the system would go down, right? Would you agree with that? That if this process is no longer adiabatic, like, you're going to kind of lose some of the energy of your system, right? So that's kind of the lesson of the Carnot engine. And I think we're done with that, but we can do some problems now. Let me see what I got. We've got 2 of these problems we can do, and then we'll get into talking about entropy. Oops. Oh boy. Click. Look at that. Oh, is it? There we go. Maybe the control key got stuck down or something. Okay, so there we go. All right. Carnot engine takes in 2,000 joules of heat from a reservoir at 500 Kelvin, does some work, and then discards some heat to a reservoir at 350 K. How much work does it do, and how much heat is discarded, and what is its efficiency? Okay, 3 questions. How much work does it do, how much heat is discarded, and what is its efficiency? All right, so it takes in 2,000 joules at 500 Kelvin, does some work, and then discards heat to reservoir at 350 Kelvin. How much work does it do? All right, how can we figure that out? How can we figure out the work that's done by this engine? We can do the easy part first. What is its efficiency? That's easy to do, right?
Yeah, I was going to say maybe efficiency would be...
All right, so the efficiency is equal to... Now, this is where we need to remember both definitions of efficiency, but I'll go ahead and write this one down first. So we do 1 minus T cold is 350, and we divide by 500. That's going to give us...
That is...
What is it?
Oh, yeah, and then it's also the work in divided by...
Yeah, exactly.
Not the work in, the work out.
Okay, so we do 1 minus 350 divide 500. Get an efficiency of 30%. So this is 0.3, or 30%. But as you stated, this is also equal to the work that's done by the engine divided by, is it Q hot or Q cold that I put down here?
It looks like it would be the... It would be the 2000. Or it would be the heat, the Q in. So it would be Q hot.
Q hot, right? Yeah, exactly. So this allows us to find the work done. This should be equal to, I believe, QH multiplied by 0.3. Sorry, it's doing that weird thing again where it tries to connect the QH. So that's going to be 2,000 joules times... So what's the 3 times 2?
Roughly 600.
Yep, 600 joules. So that's going to be the work. And now we got to figure out the heat discarded. How can we do that? I can maybe scroll up a little bit here.
Well, that is the ratio of temperatures is the same as the ratio of the heats.
Exactly. So we can just use the QC over QH equal TC over TH. So we want to solve for QC. This is going to be equal to QH was 2,000 times 350 over 500. These are both Kelvins. Let's see, 20 over 5 is 4. 4 times 35 is going to be like 700 times 2, 1,400. Does that look right?
Yeah.
There we go. Pretty easy. Just got to remember your relationships, right? Efficiency is related to 1 minus TC over TH, but we also remember that it's equal to work done by the engine divided by the heat that it takes in. And yeah, there we go. Pretty easy. Any questions?
Seems pretty fun. It's pretty straightforward. It's just the ratios, relations.
Yeah, exactly. All right, so let's try this one. This has a little more steps to it. All right, suppose 0.2 moles of an ideal diatomic gas with gamma equal to 1.4 undergoes a Carnot cycle between 227 degrees Celsius and 27 degrees Celsius, starting with a pressure of 10 times 10 to the 5 pascals. That's like, what is that, like 10% atmospheric pressure? No, 10 times atmospheric pressure. At point A, in the PV diagram above, figure 20.13. Wait, what is that? Oh, it's this figure. Okay. So it's the same figure we were using before. Let me grab it, and then we'll just make it really small. So we can kind of like point to it as we need to. Put it way up here. All right, so pressure A, that's going to correspond to this point, is that. The volume doubles during the isothermal expansion step from A to B, so the volume is going to go from V to 2V. That's from basically the left one here to the... See, that's really confusing. The fact that it's like A to B, but then this is 1. Okay, anyway. Point is that it's going to expand to twice its volume. We want to find the pressure and volume at points A, B, C, and D. Find Q, W, and delta U for each step for the entire cycle. Find the efficiency directly from the results of part B. And compare with the value calculated from equation 20.14, which is going to be the... See, I got to go back to the book again because I referenced things. 20.14 is going to probably be... Yeah, that relationship there. 1 minus TC over TH. All right. Okay. So let's go through doing this. All right, part A says to find the pressure and volume at points A, B, C, and D. So what we know so far, let's write down all the information here so that we can kind of look at it outside of the problem. So the temperatures, we got T hot. That's going to be equal to 227, but we need to add 273 to that, so I think it's going to be like 500, right? I have to unlock my phone every time I do this. It's so annoying. All right, so we take 227 plus 273, get 500. We've got TC, which is going to be 27 plus 273, which should be 300. Always have to do things in Kelvin when we're doing this stuff. We know pressure A is 10 times 10 to the 5. What else do we know? We got 2 moles, so it's N equal to 0.2 moles. And we've got gamma equal to 1.4, which feels like gamma is always 1.4 in these problems. And that's what we got. So we need to find the pressure and volume at all the points. And so on and so forth. Okay, so we know pressure A. And let's say we want to find, I don't know, what would be the easiest thing to find first? Just find the next pressure? Or is it easier to find the volume? I guess it doesn't really matter. We're going to have to use one of these two ratios regardless. We're going to be using, well, maybe I should just ask you. Which equation would we use to get started here? There's a lot of things we could do. So where do y'all want to start? Let's say, for example, we wanted to find the volume at point A. How would we do that? Ideal gas law, exactly. That's right. So normally you'd have PV equal to nRT, so we'll just do N times R times TH, and we'll divide by the pressure that they gave us. There's a lot of calculations to be done here, so I think I might try to save space on the screen by not plugging the numbers in. You can see what they are above, right? So let's just plug those numbers in and see what we get. You guys tell me what you get. I'll do the same. My hands are really hurting from writing with this stencil today. That's not a good sign. We just now starting class. Okay, 0.2 moles times 8.31, and then we multiply by TH, which is 500. We divide by PA, which is 10 times 10 to the 5th, not 10 to the 5th. Okay, I got a really small number. 8.31 to the 10 times 10 to the negative 4. I'm so tired of it doing that. 4. There we go. And that's in meters cubed. Okay, that's a VA. What should we find next? We know the pressure A, VA, and we know basically PV and T, which are a big... Okay, let's do pressure at B. What can we use to find pressure at B? Ooh, let's do something else real quick here. You're right, Kenny. We can do PV to the gamma to do that. Do we immediately know what the volume at point B is? It says the volume doubles during the isothermal expansion step A to B. We do, right? So VB is just double this. So let's write that down. So VB will be equal to 2 times VA. So that's equal to that number times 2. So it's going to be 1.66 times 10 to the negative 3. Okay. All right, then let's do PB. As you mentioned, let's come over here now. We can find the pressure at point B by writing down it's PV gamma, right? So it's PB VB to the gamma is equal to PA VA to the gamma. So then PB is going to be equal to PA multiplied by VA over VB to the gamma, which would be equal to PA, which was 10 times 10 to the 5th, and then multiplied by, it's going to be 1 over 2 basically, right? Since VB is equal to 2 VA. So we just put it in here a half raised to the 1.4, and that'll give us PB. So 10 E5 times 0.5 to the 1.4. What the hell? Oh, there we go. 378,929. Let's just write it like this. 3.79 times 10 to the 5th pascals. Pressure went down because the volume went down, right? No, other way around. Pressure went down because the volume went up. I'm going to let somebody else calculate that, make sure they get the same thing. Anyone else get the same thing? All right, great. Okay, we got pressure at A, pressure at B. Now we want to do the other side. I want to find pressure at C and pressure at D. How can we do that? Or how, well, I mean, we could find pressure or volume. Doesn't really matter. What do y'all think we should do? I think it might be easier to find volume first. What could we use to find the volume? So if I want to find VC, let's kind of segment out what we've done here. If I want to find the volume at point C, what could I do? What equation could I use then? What did I do in the derivation? How do I relate the volume at point B to the volume at point C in the derivation? Ratio of the temperature, kind of, right? It's this equation, right? Right here? Yeah. That's the one that relates VB and VC, right? Yeah, okay. So we do, for this one, what we'll do is we'll write down, let's see, so it's going to be TC VC to the gamma minus 1 should be equal to the temperature at B, which we call TH. Everything over here is TH. Everything over here is TC. So TH times VB, right? To the gamma minus 1. And then we just solve that for VC, which is going to be kind of weird because we're going to have this. But we'll get VC. I'll try not to skip too many steps here. VC to the gamma minus 1 is going to be TH over TC times VB to the gamma minus 1. And now we need to get rid of this exponent. So we'll say VC is going to be equal to so we're basically going to kind of raise both sides to the 1 over gamma minus 1 power. Wait, is that how you do it? Yeah, that's right, right? Here, let me actually write this stuff down. So we're going to raise this to the... Is it easier to raise it to the negative gamma plus 1? Or is it easier to raise it to the 1 over gamma minus 1? Both of those work, right? God, that looks awful. Did that question make sense? I think you can also raise this to the negative gamma plus 1, right? Would that work? They're equivalent to each other, though, right? 1 over gamma minus 1 is the same thing as negative gamma plus 1. So I think we'll do this one, right? Okay, so then we raise both sides to that same power. So I guess I should do it over here as well. Just write it as 1 minus gamma. Then we get TH over TC to the 1 minus gamma, and then the VB, you eliminate the power, because it's the same power on both sides. Okay, so this is going to give us a value for VC. So TH over TC was 500 over 300. We'll say 5 over 3. To the 1 minus gamma, which is 0.4. No. Negative 0.4, right? Yeah, gamma is 1.4, so 1 minus that will be negative 0.4. And then we multiply that by VB, which was that. Okay, so that should give us a value for VB. No, VC. VB is inside the equation. Okay, yeah, what's that equal to? All right, I got 1.35. Anyone else get the same thing? All right.
Yeah.
Now we need to do PC. If we know VC and we know TC, we can just use the ideal gas law to find P, the pressure, right?
Yeah.
Okay, so then the pressure at point C should be equal to N times R times temperature cold divided by volume at point C. So this will be 0.2 moles multiplied by gas constant, and then TC was 300, and we divide that by VC, which we just calculated. And we also could have done this exact same thing that we did here, because we would have all the same information as well. But either way should give us the same answer. And of course, when you have multiple ways to do something, sometimes it's nice to do both ways just to check. So if somebody else wants to do this version and check that they get the same answer that we get here, that would probably be worthwhile. So for this one, you get 0.2 times 8.31 times 300. Divide 1.35 e minus 3. 3.6, so this is going to be about 3.69 times 10 to the 5th. And now all that's left to find are the pressure and the volume at point D. Man, this is a long problem. And we've just done part A so far. So let me know if anybody gets a different answer than this. I'm just going to keep chugging along here. So now we need to do D. Just box all these things in so we can clarify where we're doing work. Okay, for point D, we're going to have to use one of these two methods here, right? For C to D, I think we use this, right? No, we can't do that, right? We've got to use this one now. And it has to be for the D to A process, right? I think what we have to do for this is if I want to find what VD or the pressure is, we need to do TC VD to the gamma minus 1 is equal to TH VA to the gamma minus 1. Would you all agree with that? You gotta be careful about when we use these, because like this is adiabatic, right? I'm just wondering, can we do this? Oh boy, I don't want to confuse you guys. Was it okay to do this? Does this only work for adiabatic processes? What do y'all think?
Sorry, which equation specifically again?
This one right here.
Oh, this one, the adiabatic, adiabatic. I mean,
I'm just thinking because the process.
I would think that, I mean, since our assumption that it is adiabatic, that we can only use it during the adiabatic process.
Yeah. So the weird part about it is that if we write down what we mean by these things, right? This is volume A, right? This is volume B. This is volume C, and this is volume D, right?
Yeah.
So to go from VA to VB, it technically is this process, right? And that is adiabatic, right? Is it though? This is where these diagrams get really confusing to me. John's saying A to B is adiabatic, you can't use that equation. That tends to be what I think as well. Instead, we should be using like an isothermal equation. Right, I have to pull up the book real quick and just to make sure that I'm not giving you guys completely off here. I've never done this problem before. So we did this stuff right. Yeah, that's right. We shouldn't have done that. This is what we should have done. That's what we should have done. Well, let's go backwards. All right. So this was wrong. Really, it's just the PV equal to PV, right? The gamma thing only shows up when it's adiabatic. Yeah, okay. So the gamma shouldn't have been there. This should have just been a 1. So this is just going to be times a half. So this is super easy. This ends up being 5. Okay, there we go. All right. So next, this was okay, I think. Right? This is definitely adiabatic. So that's fine. And then we just use ideal gas law right here, so that's fine. Those should be correct. We can even check just to make sure we're on the right track here. I don't want to get off. Come back again. VC was 59.6 times 10 to the negative 4. What did we get? Nope. So they did something different there too. What did I do wrong there? Oh, the only thing they did different was they raised it to the 1 over gamma minus 1. Maybe what I said was, maybe the math was just wrong. Is this just wrong? Don't you add the powers when you raise to the... Oh, you multiply powers when you do this. Yep, that was wrong. So my first instinct about this was right. Okay, so we should have raised this to the 1 over gamma minus 1, and this to 1 over gamma minus 1. So then this would be 1 over gamma minus 1. So it's going to be not negative 0.4, but it's going to be, and then this will be wrong too. The volume is fine though. That's going to be the same as this. Okay, so then we do 5 over 3 to the 1 over gamma minus 1 would be 0.4. now we get 5.95 times 10 to the minus 3, which is the same thing they got. Okay, so that's good. Pressure here. I'm just going to check to make sure we're doing this right because I don't want to get way off. They use this 300 over. Oh, but my numbers changed, right? The volume changed. So this is now 5.95 times 10 to the minus 3 meters cubed. And then we'll erase this. All right, so this ends up being 84,000. Right, it is 8.38. Times 10 to the 4th pascals. Okay. All right. So the last thing we were trying to do is to find the only part that's missing. We have VA, we have PA, we have VB, PB, VC, PC. So the only piece that's missing is getting VD. D to A is adiabatic, so this is okay, right? Everybody agree? Anyone disagree? This is adiabatic, right? D to A. Adiabatic. So we can use that equation. So we'll solve this for VD. So what we'll get is VD should be equal to, looks like TH over TC. This is going to be raised, it's going to be exactly like this equation here. This is going to be raised to the 1 over gamma minus 1, and then multiply by VA. So if you plug in numbers to this one, we'll get so this one's going to be 2.98. Okay, again, we're just going to check because I don't want to get off here. Yep, 29.8 times 10 to the negative 4 is the same thing. Okay, so that's VD. And then to find the pressure, we again use the ideal gas law. Pressure at point D is going to be nRT TC over here, divided by VD. So using the number that we just got, TC is 300, and divide by VD, which is what we just calculated. We get 167, so this is going to be 1.67 times 10 to the 5th pascals. Okay. All right. Any questions about that part? That's part A. All of that stuff was part A. Sorry for the mistakes that I was making there. I think it's valuable to make mistakes in front of you so that you guys understand that I'm just as bad at physics as you guys all are probably and make mistakes all the time. And yeah, you have to stop and think about every step, and I didn't stop and think about the fact that this wasn't adiabatic. So I'm glad we caught that. Okay, any questions? All right, it's already 11 o'clock. Do you want to finish this problem, or do you want to take a break right now? What do y'all think? During the break, you could probably try to work it out yourself if you really want to. You want to do that? No response. Are you all there? We're going to take a break.